So yeah, and you know, one thing that's actually really kind of fun, and it has very little to do with this particular sequence, but if you want to see some neat patterns, get out a grid or a piece of graph paper, right, and write down the multiplication table. I know it sounds kind of silly, but if you look at the multiplication table, like just look at 10 by 10 multiplication table. So and you look at this, okay? Well, obviously the perfect squares are along the diagonal. 7 times 7, 6 times 6, blah, 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 right? Okay. Then, if you look at diagonal entries from each other, okay? So let's do a small little break. Let's do 5, 6, 7, and 5, 6, 7, just for giggles, right? So if we do this, we get 25, 30, 35, 30, 36, and 42, 35, and 42, and 39. Okay. No big surprise here that what we're looking at is a degree of symmetry because we have the commutative property, right? 3 times 5 is 5 times 3, so it would be symmetric. Okay? But take a step back and look 1 unit away. Coincidence? Maybe. Oh, Rocco, what is this? Yeah, of course it's May. Check it out as that, right? So 16, 20, 24, 28, and then of course we're going down 20, 24, 28. Sorcery. In fact, it's not a coincidence. In fact, it's a simple feature called the difference of squares, which you learned in Algebra 2. If you think about what this is, that's 6 times 4. Well, that's 6 times 4 is really 5 plus 1 times 5 minus 1, and then we get 5 squared minus 5 plus 5 minus 1. Okay. So anything slightly off of that diagonal is only 1 unit away. And you can use this to do some really cool mental math. Okay? And in fact, if you take it a further step out and you go to, say, just move these, move it up. You're taking 2 steps away, right? From 5 squared, you go 2 steps away from it, and you're 4 away, which is 2 squared. Remember, now we're dealing with, 3 minus 7, 3 times 7. 5 minus 2, 5 plus 2 equals, very quickly, 5 squared minus 2 squared. It's the difference of squares. Remember, if it was like x plus 3 and x minus 3, it would be x squared minus 9. Right? So this is a nice little quick pattern. And what's also really cool, if you're interested in looking at it, is just the last digit of the multiplication. Throw away all of the other digits. Just the last digit. You guys have been staring at the multiplication table your whole lives. You know, since you were like 2 months old, you've been staring at multiplication tables. Nobody looked at just the last digit. Except for crazy people. And in fact, if you look at the whole thing, there's some really cool patterns. Really neat patterns. 5. Well, think about it. 0, 5, 0, 5, 0, 5, all the way down the road, right? And it lands on 5 when it's odd, and it lands on even when it lands on 0 when it's even. And if you look at, say, for example, the 7th, just the 7th, 7's times table. 7, and then what will my next number be? 4. What's next? 8. Keep going. 5. Next. 2. All of the digits are represented. But look at, say, the 3's times table. Okay, so what do we have? We have 3, 6, get ourselves confused. 9, 2, 8. And 0. All of the numbers are represented. Is that true in all cases? How about, say, for example, 4? 4, 8, next. 2, 0. See? So some always have a sequence of numbers that repeats. Go to the group board. Go get a drink of water. Yeah, no problem. That reminds me. So if you look at the entire table, you'll see some really cool stuff. So one of these days when you're sitting in English class and you're totally bored, pull out a piece of paper and look at that list. It's really kind of neat. Or not English, of course, never English. Biology's fine though. So anyway, that's some pretty cool stuff. All right, let's pull out our notes from last class because I want to go into some more induction. All right. All right, so today I want to go over some more examples of induction and see if we can come up with a nice little set of problems to see if we can see how we're doing on all of this. If you want to work on the boards, you're more than welcome. All right. Oh, by the way, I want to yell at all of you for recursion. You guys goofed recursion, and I have to go back in my notes and see if I screwed it up when I explained it to you. But almost nobody forgot about the base case of induction, recursion. So, like, if we have, say, the sequence. No. Like, okay, like, let's just do this. Okay, so this is my sequence, right? All right. If I wanted to do this recursively, so what are we doing? Is this arithmetic or geometric? It's arithmetic, and I'm adding 5, right? Okay. So if I wanted to do this, we'll do this really quickly. This was actually, I think, number 8, letter A. So if I wanted to do this recursively, I say A1 equals -3. Everybody forgot that thing. And then A to the n is A to the n minus 1 plus 5. That's recursive. Okay? You got to say where you start. You're telling me how to walk there, but you're not telling me where you start. Okay? So please, please, please don't forget that. It's kind of like when we started off the Fibonacci sequence. You have to say, hey, the first number is 1, and then the second number is 1, and then every number after that is the sum of the two guys before it. You know? Now, if I wanted to do this guy explicitly, sorry, yeah, that's recursive. Now, explicit would be starting with the formula for it. So A to the n is equal to A1 plus D n minus 1. And plug all your stuff in. Okay, now, you're going to be with me for the next 2 years. We're only 20% through the first school year. Okay, we've got a long time left to go. I know, only 20%. Darn, it sucks. Yeah, we're on the 30th day of school, and there are 180 school days. No, gosh, it's 1/6, so 18%. We're good, even less. Woohoo! All right, don't we love it? But 16.6%? Yeah, it is. Right. Gosh, math. I can't math today. To borrow somebody's words. If you were looking at this, please don't leave this as your answer. Okay? Go ahead and take the extra step and expand it out a little bit. Okay? And that would be your final honest to God answer if you're looking for an explicit formula. What? Yeah. I really want to know that the reciprocal of 6 is 0.1666 bars. Simply because if you're really interested in that another really cool table, look at the reciprocals of all the primes. Fractions of the prime number, when you flip them upside down, you'll find out, and here's actually a really cool thing if anybody's interested in finding out. If a number, okay, check this out, this will blow your mind. If a number's decimal stops, okay, remember what the rational number said. If it never repeats and doesn't stop, it's irrational, right? That's actually not the definition, it's actually just a feature of the irrationals. But if a number actually, honest to God, stops, okay, so if I say that 1 over n, okay, if I really wanted to write it mathematically, 1 over n log of this is less than infinity, okay? So that means if I take the reciprocal and I take the log of it, okay, base 10, what is that saying? What? Well, wait a minute, Rocco, who cares? And why log base 10? Okay. Call out your phones or grab a calculator and do this. Okay, I just randomly threw that number out there. Find out what goofy, oddball thing. Everybody's got a log button on their calculator, and if not, here, grab one. It's log base 10 now, okay? 35728. Okay? And round that number. What do you get? To a whole number. How many digits does that number have? That number on the board. Ah, wait a minute, sorcery again. Ah. I'll try. Take the log base 10 of that goofy thing. It is sorcery, is it not? 1, 2, 3, 4, 5, 6, 7, 8, 9. This thing rounds to 9. No. The reason why is because we work in base number in a number system of base 10. Okay. So this thing, okay, is somewhere between. If you think about it, can I just make my life easy here? This is a 9-digit number, right? This number, whatever it is somewhere. Let's call this n. All right. N is between 10 to the 10th, right? And 10 to the 9th, right? Somewhere falling in between those two numbers, right? So let's take the log of this thing, right? What do we get? Should be between 8 and 9. 10 to the 9th. Oh, because it is. This number would be 3.5 blah 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 times 10 to the 8th, right? True? Think about your significant figures in chemistry, right? If I move my decimal point, 1, 2, 3, 4, 5, 6, 7, 8, right? Yeah, I didn't really do math today. Maybe I should. And this is, again, so if you're looking for the number of digits this beast has, if you don't know how big your number really is, take a log of it. And that'll just roughly eyeball tell you how many digits you're playing with. Okay? Does that make sense? Because it's how many tens go into it. That's what it's saying, roughly. Okay? Because it's 10 to the something or other gives me this beast. So that if I say 10 to the 5th, that's saying I'm going to have 5 zeros and some stuff. Right? This number says go out 8 digits and then some stuff. You know, it's 10 to the 8th plus a little bit. And that little bit is your 0.55 in your log when you took it. And you can play with it. It's actually really quite fun. All right. And in fact, try this number. This actually is perfect to today's lesson. What's that? What is it? 4.5.49968. Blah 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 blah. Right? Okay. Well, first of all, a couple of features. 1, 2, 3, 4, 5. Really darn close to half, right? Right? Take the square root of 10. Right. In fact, it's 3.16. Right? True? So, yeah, I know. So what does that tell us? Okay, if we look at the graph of a log, okay, and we look at where 3 is, sorry, where 10 is. We would be there. But correct this. No, I've got my axes. Man, Mark's gonna be laughing his butt off because he's gonna be sitting there like, okay, Rocco's after mine, and it was a good day for me to not be there.
Oh my God.
All right. So what is going on here is that the graph of a log grows slowly, okay? But it grows. You have to kind of put your brain around the logarithm in a sense. Okay. What are we actually saying in a log-based whatever? We're saying how many powers of what? Okay. Now, I'm seeing, if I look back in my memory on that homework assignment, I'm still seeing people not doing stuff like, something like this, and then doing this. No bueno here. Don't do this. I'm seeing this happen a bunch. Okay, can't do that. All right. A log is it's something you do not to a number, but to a side. Okay. You do that to the side of the number. Okay. The left-hand side or the right-hand side. So and we don't have a rule for this. We don't have a rule for that. Okay, you can't do anything with it. Okay, because log doesn't work on addition. Log works on multiplication, an exponent. So we have to take the top and turn it into a single beast before we can take a log of either side. Okay, you would do this. Actually, you can't. With this, you would have to do. Yeah. You would just do 125 equals 5 to 7, whatever the heck 5 to 7 is. Don't tell me. 5 to the 4th is 625. 3,125. 1,505. 625. 15625, and then one more time would be 7, 8, 3, 125. 125. Great. Yeah, that's it. Great. Someone read back to me because I just forgot the number. 7, 8, 1, 2, 5. And then you would subtract. Okay, so yeah. You can't really play with the upper function. You can't take a log like that. So I kind of want to bury that into everybody's head a little bit. All right, induction. So the general steps of an induction. Did I give you Steve last time? Or you
We never actually
wrote out.
Yeah.
Okay, let's kind of get a flow chart. Okay, like a process recipe of it.
So
Oh, well, it is. Well, it is hard to describe, but let's go through it nonetheless. One, state what you're trying to prove. Or state the goal. I'm going to prove that blah, blah, blah is divisible by 5, always. Or I'm going to prove that the sum of all this stuff is greater than the price of X each time. Okay. 2. State the assumption. No. Let's do the base case first. There may be more than one base case. Okay. You might need to do the base case 2 times. There are some proofs that require what is called strong induction. And in strong induction, you are saying that not only can you take a step, but you can take a step and then jump. You know, you can do 2 things in a step rather than just 1. Okay, sir. You would say the base case is 1 and then the base case is 2. You know, you would do 2. Or you could say, like, for example, if I said every multiple of 4 is divisible by 2, okay, then you would start with the first multiple of 4. Okay, 0. Well, 0 might not be enough for my proof. I might need 0 and then 1. So in that case, 4. I would have to test it on 0, and I would test it on 4. And if it holds for both, that's wonderful. Okay. All right. Third, state the assumption, and state what you're trying to prove. Show me what the k+1 thing is, okay? Because you want to say to the reader, hey, look, I'm going to go down this path. And when I get to something that looks like this, when I find my Mitzelplick at the end of the rainbow, I've won the game. Well, what the heck does a Mitzelplick look like? This is what a Mitzelplick looks like. You have to show me what your answer is going to look like. Because if you don't, if the reader doesn't know that you've succeeded, then it isn't really a proof. You know, if I say to you, hey, there's a leprechaun at the end of every rainbow, let's go prove it. Well, the question is, what the heck is a leprechaun look like? Here's one. It'll grant you 3 wishes. Right. But the thing of it is that if you've never seen what a leprechaun is, then how do you know that that isn't a leprechaun? See what I mean?
Yeah.
Okay. So that's why you have to show me what the k+1 thing looks like, so that when we get there, we know we can beat the crap out of this little green guy and get some gold. Okay. Great. Next. That was recorded. Oops. Next. All right. All right. Then we state the assumption. Okay, to do this, we begin with the assumption. So, and that's usually the K case, right? You know, we assume it's true up until K, and now we're going to start taking steps and show that the next step works too. Okay? Properly installed or it's the wrong model more, because it's trying to work, and then it says this is good. So I think it might be a model number issue, or maybe it's not saved. Might not be saved right or something like that, or maybe it's not getting triggered. You know, that the lamp is installed properly, because I mean apparently when it was put in, it worked for a company, and now it's not.
Right.
That's the only thing I can think of. Because otherwise,
I just want to see if I don't think it's like a fan failure, right, or anything.
it doesn't look like a fan failure.
It sounds like fan failure.
Right, and actually when I unplugged it and let it sit and then plugged it back in, it's working with the cameras and then it got back with the big on.
Yeah. I just want to see if you were confirming something. I just want to see if you were thinking of something straight. I think you'd be very good at projectile.
Right, that's good. But no, I haven't, I didn't see any, it didn't look like software issue that we had to work with. It's not the computer side.
Yeah, it's important for you.
Yeah.
It's all a projector.
And the whole being using to replace the substrate. And you know what I would do first? Anything, unscrew it, pull it out, shake it off, make sure there's no dust around in there. It might just be contact. See, yeah, because I know that it's not sitting properly, it's not like touching all the right places. It might not fire at the right level. So it's just when you take it apart and sit in that long, that whole thing, it might be dust. It might just be something simple as that. All right, ladies and gentlemen, let's get back to work. Sorry. But every now and then I got it. So yeah. Okay, so this is the assumption. Then 5. What you try to do at this point is figure out how to turn the left-hand side of K, of the K case, into the left-hand side of the K plus 1 case. And you have to do the same thing for the right-hand side. So, sometimes, I mean, obviously what we have to do is maintain equality. So if you're going to multiply something on both sides, so if you're going to multiply something on the left, you need to do it on the right. You can't just say, hey, hey, look, left-hand side, you're not big enough. Here, multiply by 2. Boom, done. Okay, next. You can't do that. You have to do that to both sides. So, but you usually manipulate them separately. Pixie dust is a very important mathematical operation. Oh yeah, that's okay. At Patriot, they still circulate my notes from their AP balance. Okay, yeah, I have students paid for my tutoring services by selling my notes. But I thought that was really it's an interesting idea. Often separately. Think about it. You pay me, and then you get, I mean, you probably paid for me. But years later, I had somebody look at my work and say, "I know that handwriting," and actually pull out notes that were mine for people. Manipulate each often separately to make. Okay. That is a lot of algebra, usually. And this is where the real math comes in step 5. Okay. And there's usually like the conclusionary statement saying, we have done what we wish to do, quid erat demonstrandum, and you move on. Okay. We good? Let's do it. lost his immune. Try to solve this on your own. Yes.
Yeah, no, it's not Jack.
I just think he's got, well, he's only got one class.
You can have my Friday lecture.
My Thursday lecture, so I'm not going to be here. We did flex this week. What was the last flex?
We don't have flex anymore.
We have 6.
We have flex on Friday.
We have, yeah, it was what's tomorrow. It's not really what it's no one, 4 more hours.
Something like that. All right, so let's look at this. All right. So if you do the base case, let's see what happens. Okay. Try this. Actually, you know what? Try this one on your own now that Marcus has turned the video back on. So try this. On the boards. Go for it. Now I'm going to pause the video, and Marcus can be like, oh. So the base case holds. Next, we assume that the statement holds up to some integer k. We attempt to prove the k plus 1 case, which is of the form. All right, we're going to fill Marcus in. So we added k plus 1 times k plus 1 factorial to both sides. So my left-hand side looks good now, right? My left-hand side is done. And I've added it to both sides. So we have to think to ourselves for a minute, what exactly am I looking at? Okay, if this is the goal, can we look at that for a second and say, okay, it's really saying k plus 2 factorial, right? Isn't that really what that is? Look at what I just started. It's k plus 1 factorial. It's really k plus 2 factorial, right? Okay, and then I'm subtracting 1. Okay, fine. Well, for a second, I can sit there and be all happy and warm and fuzzy that I have a minus 1 already. That part is done. I don't have to fool with that. So what I need to do is I need to turn that k plus 1 factorial and that k plus 1 times k plus 1 factorial into k plus 2 factorial. Ten of them. Because if I can get to k plus 2 factorial, I'm done. And all that stuff is still here. What is that? Well, what the heck is k plus 2 factorial? K plus 2 factorial is a whole bunch of stuff, but it's k factorial times k plus 1 factorial, no, times k plus 1 times k plus 2. That's really what it is, if you think about it. Actually. That's what the factorial is. If I say 10 factorial, that's 7 factorial, which is shortcut, times 8 times 9 times 10. Yes? You agree? By your teacher. Excellent, me too. So, if we just say, for example, like this, you have to put your brain around this factorial. This is 12 factorial, right? That's 10 times 11 times 12. Okay? See what I mean? How did I get what? That's what it looks like. That's really what k plus 2 factorial is. That's my goal. The k plus 2 factorial is what I want. So it's a good thing to know what I'm looking for. So when I find that leprechaun, and I sniff him out, because we all know how leprechauns smell. If you smell that leprechaun, you can grab him and say that you won. That's your total. Gosh, man. Staying. Okay. So, can we do this? Look, how about this? That's also true. That's the same as saying this. So look at what you have right there in this line. How do I turn this? How do I turn that into k plus 2? What do you have? Yeah. And you have 2k plus 1 factorials, right? They're in both terms. What's that? Yes. Say it.
I said it's that. I didn't say anything.
Darn. Because it was right.
We live in one draft.
What would you do to a quadrant?
I don't know.
Well, you can't really FOIL into a factorial because factorial is a function by itself. But what would you do to a factorial? To a quadrant? If you were looking for a truth. Thank you. That's the word I need. What do we have when we factor out a k plus 1? Marcus would know. Marcus is sitting there screaming and yelling, it's 1 plus k plus 1. 1 plus k plus 1. Good, Marcus. Well done. See, because what I did was I factored GCD out of both pieces. Light bulb.
Wait, where's the factorial?
No, I factored it out. I had a k plus 1 factorial in both numbers. So I factored it out because it was a GCD in both terms. Look, guys. Factoring. I've heard of such mystical beasts. They go roaming around the mathematical countryside. It's called factoring. You get an ooh and an ah. You can too. You too, Marcus. Ooh.
Oh, okay.
Ah.
Sorry.
Do you see? But do you understand? You see where how I got it?
Yeah.
All right. Well, so. So now, just do a little rearranging, and you've got your final form, and then you're done.
Can we rearrange it again?
It's called the associative property. Right? True. Remember what our goal is. place. That's the problem. All right, so you see how this works? See how I did it? Which is the desired form. Yes. It's like space facing twinkle.
Oh.
Which is the desired form. So by the power vested in me by the principle of mathematical induction, I hereby declare this proof. Yes.
Why didn't we?
K plus 1 factorial is just a number. It's nothing magic. It's nothing. It's just a number. It's. I mean, if you think about it, let's do it with a concrete example. Okay. 12 factorial is really easy. Okay. Let's do it with a smaller number so we can write it all out. 5 factorial. Right? We agree? So, if I said do you agree? Yes. All right. So, 5 factorial is 120. 5 times 4 times 3 times 2 is 120. Do you agree? I'm not lying to you.
Okay.
Now we're solid?
Yeah, I think that one.
And then this would be in this case 7. See how that works? Okay. Next. No, sorry.
Yeah, I don't have to go to that class. We don't have to, we run on. Because English, it's like our group things today. Yeah, our group thing is today. Yeah. Psychology things today. It's not a group.
Sam, this one's just for you. I mean, everyone else can do it, but this one's for you. So we're going to, now let's test the base case and see that it holds. What would the base case be, by the way? 4.
What does he agree to before?
No, for all numbers greater than 4, so it must be 5, right? Marcus would have. So 2 to the 5th is, right? Okay? All right, so we're trying to prove, and we're going to do this one really fast, so the base case holds. Right. Now, we are looking for the k plus, we assume that everything up to the k case holds, and we're trying to prove the k plus 1 case. Everybody right now, write down what the k plus 1 case looks like. What does this unicorn look like? It's just as mythical and magical. Right, yeah. Right? Ah, yes, we have inequality. So the k plus 1 case looks like 2 to the k plus 1 is greater than n plus, not n, k. Squared. Okay, so we're going to start, so we start with the assumption. So now, here's where pixie dust comes in, and you need to turn this into that and this into that. So this episode of the Ronco Show has been brought to you by the Principle of Mathematical Induction and our friends, unicorns and leprechauns. Have a good day, Marcus.